Hi everyone, today I'll be talking about curve sketching. So this is the table of contents. My slides will be separated into 5 sections. I will begin with increasing and decreasing functions, followed by critical points, asymptotes of rational functions, concavity and point of inflection, and lastly, algorithm for curve sketching. So I will start with increasing and decreasing functions. The behavior of the functions can be determined by the increasing or decreasing intervals. So as you can see in the graph, this graph is increasing as the first x value is smaller than the second x value, and the function of the first x value is also smaller than the function of the second value. This indicating that the function is increasing. By looking at the trend of the graph, it is rising from the left to the right. This also indicates that the function is increasing. In this graph, the first x value is also smaller than the second x value. However, for this time, the function of the first x value is larger than the function of the second x value. By this, it indicates that the function is decreasing. And looking at the trend of the graph, the line is falling from the left to the right, which also indicates that the function is decreasing. For functions that are continuous and differentiable, the intervals of increasing and decreasing y values can be determined by using the first derivative test. If the first derivative fx is larger than 0, the fx will be increasing. Vice versa, if the first derivative of the fx is smaller than 0, the fx will be decreasing on the intervals. So by looking at the table, when the dy dx is smaller than 0, the slope of tangents will be negative. This indicates that the fx will be decreasing. And when the dy dx value is larger than 0, the slope of tangents will be positive. And this will indicate that the fx value is increasing. Now I'll be talking about critical points. What's the difference between local extrema and absolute extrema? So basically, local extrema is a point where the function at which it is the maximum or the minimum value of the neighboring x value. And for absolute extrema is basically the largest value or the smallest value of the function in the entire intervals. So as you can see in the graph, local maximum and local minimum is the peak of the curve. However, both of them are only the maximum or minimum of the neighboring x value. However, from absolute minimum and absolute maximum, both of them are the largest and the smallest value of the entire graph. So we will be using first derivative test to find the critical points. First derivative test is basically a test for local minimum or local maximum point by letting the fx value to be differentiate n equals to 0. Critical numbers is a number in the domain of fx such that the derivative of fx is equals to 0 or undefined. And the critical point is the point correspond to the local or absolute extrema. So as you can see in both of the graph, the first graph has a local minimum and the second graph has a local maximum. So for critical points that do not change sign at the C value, which is the critical number, it is neither a local extrema. By looking at the graph below, when we are moving from left to the right of the x value, the first derivative of fx will change its signs from negative to positive. This indicates that the fx will have a local minimum at the critical point. And the local minimum value locations is determined by using the critical number if the functions of the critical number is smaller than the functions of the x value, neighboring x value. And when the first derivative functions changes its signs from positive to negative, the fx graph will have a local maximum at the critical point. And the location of the local maximum value for the function is also determined by the critical number when the function of the critical number is larger than the neighboring functions of x. Now I'll be explaining ways to find the local extremal values of the function. So first of all, we will have to find the critical numbers by using the first derivative test. After that, we will be using the same test to analyze whether the function is increasing or decreasing on each of the critical number. And lastly, we will be using the second derivative test to indicate whether the critical numbers locates a local maximum value or a local minimum value, or neither. So here's an example of how to find a critical point. So first of all, we will be differentiating the equation. After that, we will be equating the equations that has already been differentiated to 0. And by that, we can find the x value. So for this question, the critical point is equals to -2, 0, and 2. For this section, I'll be talking about asymptotes of the rational function. So what is a rational function? Rational function is basically a function that is created by dividing two polynomial functions in the form of px over qx, where both of them are polynomials, and px is the numerator and qx is the denominator, and qx can never be equals to 0. For asymptote is basically a line that a curve will approach as the curve is moving to infinity. However, the line and the curve will never meet at any infinite distance. There's 3 types of asymptote: vertical asymptote, horizontal asymptote, and lastly, oblique asymptote. For vertical asymptote, it can be found by equating QC equals to 0. So when the denominator is equals to 0, the x value found will be equals to the vertical asymptote. So for the notation, when the x value is larger than the vertical asymptote, the x will be approaching the c, which is the vertical asymptote from the right. And when the x value is smaller than the vertical asymptote, the x will be approaching the vertical asymptote from the left. So this graph will be showing how the relationship between the vertical asymptote and the infinite limits. So when the x value is smaller than the vertical asymptote, it will be approaching from the left. And when the x value is larger than the vertical asymptote, it will be approaching from the right. When the x value that is smaller than the vertical asymptote and it has a larger function, it will be approaching the vertical asymptote from a positive infinity. However, if the x value is larger than the vertical asymptote, however, the functions of the x value is negative. Therefore, it will be approaching the vertical asymptote from a negative infinity. So here's an example questions on how to find the vertical asymptote of the equation. So first of all, we have to factorize them and put them in brackets. And by that, we can find the wholes, which is the discontinuity. Since both numerator and denominator consist of x minus 2, therefore it's the common factor, it needs to be cancelled out. And therefore, x plus 2 is the remaining factor of the denominator. We will be equating the x plus 2 to 0, and by that we can find that x is equals to -2. And the vertical asymptote will be x equals to -2. To find the limit of infinity, first of all, we have to find value of x that is smaller than -2 and substituting the value into the fx. By that, we can find the answer is smaller than 0, and it is approaching the vertical asymptote from -infinity. And for values that is larger than -2, after substituting it into the functions, we can find that the answer is larger than 0, and therefore it is approaching the vertical asymptote from a positive infinity. Horizontal asymptotes describes the behavior of the graph as the x is approaching infinity, a positive infinity, or negative infinity. So in the rational function, horizontal asymptotes only occur when the degree of the numerator is less than or equals to the degree of the denominator. So there's 3 possibilities for horizontal asymptote. The first is when the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote will be equals to 0. And when the degree of both numerator and denominator is equals, they will have a horizontal asymptote by dividing the leading coefficients by the highest degree term. And when the degree of the numerator is larger than the degree of the denominator, the graph will have no horizontal asymptote. However, there will be an oblique asymptote. For reciprocal functions, it will have a horizontal asymptote at 0. For horizontal asymptote and the relationship between the limits at infinity, so first of all, we will use the notation limit to find the horizontal asymptote. By that, y equals to L will be the horizontal asymptote. After that, we will use a very large value or a very small value. So for example, a very large value will be 1000. By substituting the 1000 value into the function, we will get an answer that is larger than the horizontal asymptote. The graph will be approaching the horizontal asymptote from above. If the answer that we obtain is smaller than the horizontal asymptote, the graph will be approaching the horizontal asymptote from below. So here's an work example. So to find the horizontal asymptote of this equation, first of all, both of the degree of the numerator and the degree of the denominator is the same. Therefore, by using the limits of infinity, we can find that the horizontal asymptote is equals to 1. After that, we will be substituting a very large value, which is 1000, into the function. And the answer of the functions is larger than the horizontal asymptote. Therefore, the graph is approaching the horizontal asymptote from above. And when we substitute a very small value, which is negative 1000, into the functions, we found out that the answer is smaller than 1. Therefore, the graph is approaching the horizontal asymptote from below. Lastly, this is oblique asymptote, which is also known as slanted asymptote. It can only occur when the degree of the numerator is exactly 1 more than the degree of the denominator. So to find the equation of the oblique asymptote, we will be using the long division method by dividing the numerator by the denominator to obtain the quotient, which is mx plus c, with a remainder rx. The quotient will be the equation for the oblique asymptote. Now I'll be talking about concavity and point of inflection. So the second derivative test is used to find whether the fx has a local minimum value or a local maximum value. So the test is used to analyze the behavior at the critical point. So when the second derivative test of fc is larger than 0, the fx will have a local minimum value and the graph will be concaving outward. And however, when the second derivative of fc is smaller than 0, the fc will have a local maximum value and the graph will be concaving downward. When the second derivative xc is equals to 0, the nature of the critical points cannot be determined without further work. To find the point of inflection, the second derivative of fx will changes its signs at the critical point on the graph. The curve will be changing from concaving downward to concaving outward, or vice versa, concaving outward to concaving downward. Or the point of inflection on the graph must occur when the second derivative test is equals to 0 or is undefined. Lastly, I'll be explaining how to sketch a curve, which is basically the algorithm for curve sketching. So first of all, we will use the function to determine the domain, discontinuities, x and y intercept, and also to find any asymptotes and determine the behavior of the function relative to the asymptote. For the example question that I use, it is a polynomial function. It is a polynomial function graph. Therefore, there will not be any asymptotes. So for these equations, we will be only finding the x-intercept and y-intercept. After that, we will use the first derivative test, which is dy dx, to find the critical numbers, c, and we will use it to determine whether the function is increasing or decreasing. And we will use it to identify any local extrema. So for the example equation that I use, we will find the critical points by derivating the equations and equals the equations to 0. After that, we will get to find both x value. After that, we will use a second derivative to determine whether the graph is concaving downward or upward. And we will be using the second derivative test to find the point of inflection and also to identify the local extrema. So as the example shown, the second derivative is used to find the local minimum and also the local maximum. By equating the second derivative fx to 0, we can find that the x value of the point of inflection. And lastly, we will use a table to find out whether the graph of fx is concaving downward, upward, or whether it is a point of inflection. We will be calculating the y value of the critical points and also the point of inflection. And lastly, after gathering all the information, we will use the information to sketch the graph. That's all from me. Thank you for listening.